Hi, my name is Peter Gao, and I am a staff scientist at the Carnegie Earth and Planets Laboratory. Today, I will be telling you about my JWST Cycle 1 program, which focuses on a unique class of exoplanets nicknamed superpuffs. Superpuffs have masses of only a few times that of Earth, but sizes like those of the giant planets in the solar system. This gives them extremely low densities. For reference, rocky planets like Earth and Venus have densities like those of, not surprisingly, rocks and metals, while giant planets like Jupiter and Saturn have densities like that of water. Superpuffs, on the other hand, have densities more like those of cotton candy or styrofoam, implying that a great deal of their mass is made up of light gases like hydrogen and helium. Not only does this present a problem for their formation, how did they capture all that gas given their low gravity? But also it makes it difficult for them to hold on to all that gas over their lifetime. And so it is a mystery why some superpuffs even exist. One reasoned hypothesis for the nature of superpuffs is that they are not as big as we think they are, as the sizes of superpuffs are measured through the transit method, where we detect the slight dimming of stars as their planets transit in front of them. If superpuffs have high altitude layers of clouds and hazes, or even a ring like Saturn's that can make them look bigger, then it's possible that their actual density is much higher. I will use JWST to test this hypothesis by measuring the transmission spectrum of a superpuff, Kepler-51b. A transmission spectrum is just a transit, but observed over a range of wavelengths. This is important because clouds and haze layers and rings affect the transmission spectra of exoplanets in different ways, and so we hope our observations can differentiate between these scenarios. We also hope to capture any signatures of gases in the atmosphere. Different gases, such as water vapor, methane, or carbon dioxide, all have different fingerprints that they leave on the transmission spectrum. If we can detect these signatures, then we can say something about the atmospheric composition and perhaps how the atmosphere and the planet formed and evolved.